So today I want to tell you about the mathematical journey I went on after my first video on connected lights. If you recall, these are lights in a connected network where flipping the switch on one light will toggle the on-off state of itself and its neighbors. We played with the lights in a row, so I wondered what happens if we put them in a loop, like this simple setup of 4 lights in a loop. There I noticed something curious. If we remember how to turn on the top right light individually with these switches, we can make any pattern we want. If we want this other light on, we just rotate the set of switches. If we want 2 of them on, combine the 2 sets of switches and remove the ones we flipped twice, because flipping any switch twice does nothing. Well, that's convenient, because checking all patterns in the loop setup becomes as simple as checking just one light. Then I tried the loop with 6 lights. Makes sense, I suppose. If you recall from the last video, if we can find 2 sets of switches to turn on all the lights, there must be some patterns we can't get to. In the loop of 6, we have 3 sets of switches to turn on all the lights. This feels strange. One pattern having 3 sets of switches feels like every pattern that works should have 3 sets of switches. Which means only 1/3 of all possible patterns are achievable. But the total number of patterns is 2 to the power of 6. Or 64, which is not a multiple of 3. So we can make a fraction of a pattern, or a pattern can be partially achievable. Something's not right here. So I listed all the patterns we can make starting with all lights off. All of them, one at a time. That means we should have 4 sets of switches for every pattern. Whew, math makes sense again. Now the question becomes, for which loop sizes are there patterns that are impossible to make starting with all lights off? And for those loops, is it always 1/4 of the patterns that work? Let me know what you think in the comments below, and until next time, stay curious.